Electrical noise is anything signal that's on the circuit that you don't want. So like when you look at it at a DC, if you were to look at it on an oscilloscope on DC, what you'd like to see is a perfectly straight line. And what you'll probably see is some little jaggies. And those little jaggies are the noise introduced by various things. Okay. Now, and so I'm about to move on to grounding because there's two types of grounding actually. All right, and there's a big distinction here. The first type of grounding is what's required by the NEC, National Electric Code. And the goal in grounding by the NEC is to make sure that no two pieces of metal are ever at a voltage difference that could hurt you. In other words, you wouldn't want to touch this panel and touch, say, this metal table and find out there's 120 volts between the two, right? Because one of them touched a hot wire and the other one was grounded. So the goal in NEC is to simply tie all the metal, all the non-conductors together everywhere. So like in your receptacles and your switches and stuff, and in the electrical panel, everything is tied together as much as possible. The consequence of this is that when there's a problem, like a short circuit, the motor goes bad, your hair dryer goes bad, goes to ground, okay? The current has to go someplace. And in the case of AC, the current can be really high. The breakers in your house are rated to break a current of 5,000 amps. And you say, wow, you're going to get 5,000. You can get several thousand amps without any problem at all in a normal house service, okay? So the question is so where does the current go? And the answer is everywhere. In other words, every ground wire in your house, when you have a ground fault, every ground wire will see some current flowing on it. The goal is to simply make sure that something doesn't become energized so it can hurt you, okay? And that's the entire goal of power grounding. Now, when you tie things together like this, you form what are called ground loops. And a ground loop is, where you have more than one path for the power to travel on. And in the case of safety grounding, the code is make as many ground loops as you can. Make every piece of metal tied to every other piece of metal that's grounded so that the two can never be at a different voltage, right? And then, as I said, when you have a fault, current flows everywhere. It's like in a big factory, if a motor goes bad and goes to ground and puts a huge amount of current into the ground for a few seconds before a breaker trips, that fault goes through the entire electrical system of the building, at the ground system. It goes onto the frame of the building, it goes to the plumbing, it goes everywhere, all right? So you have to make sure that that it eventually dissipates, but more importantly, that no 2 points close together can be at a different voltage so you could get a shock, okay? So this is safety grounding, all right? And going back years and years ago, when I was a little kid, one of the first things my dad taught me, and which I still teach everybody that I work with on electric panels, is the first wires you should connect in any panel are the ground wires, all right? Reason one, if you don't do them right away, you're probably going to forget some, in which case you're going to have some safety issues, okay? So the second thing is that grounds aren't any part of your controls. They're a safety thing. So once you put them in, you never deal with them again. You don't touch them again. You don't ever change them. You don't lift them. They're just, they're there and they stay. So that means that you don't want to put the ground wires in last on top of all your control wiring. Because now if you want to, sometimes you do make changes in the control wiring and you don't want to dig through the bundle of wires to get to the wires you want. So when this panel was wired, this was one was done by Andrew. We first did all the ground wires. So every VFD here has a ground wire on it, right? And they all go down to the ground block here. And we have ground blocks that tie to the DIN rails, and they're all tied together. And there's a ground wire on the PLC, and there's a ground wire on this. So we did all of those grounds first, and you can see there's quite a pile of them, but they're in the bottom underneath, okay? And that's where they belong. The ground wires should be buried. My dad's saying was bury the ground. Then the other side is the commons. And we have, commons are, in power you need a complete circuit for energy to flow. So you always have something that's considered the hot, which is that it could be 120 volts or 240. And it can also mean, it's the same term for DC, right? And so you always have a hot and you have a return. So power goes out through a device and comes back on the return or the common, all right? So in the case of AC, we have a common here. And again, we hooked up the commons first. You see we have a common block down here. And this terminal block has jumpers in it. And the purpose of that is just to give us a place to connect multiple wires together without wire nuts and things like that. So we use terminal blocks with jumpers in them to make a common block for the AC. And then everything that's AC, that's 120 volt AC in here, comes to the common block. All right? Now, same deal as the grounds. You never switch the commons. You don't put controls in the commons on 120 volt AC. In your house, none of the switches switch the common wire. They all switch the hot wire. Okay? So that's the case everywhere in your house and everywhere else. Now, in the case of power, of service wiring, the service panel in your house has the neutral and the hot wire, and the grounds tied together, all right? And that's the only place it gets tied together. And if somebody puts a sub panel in your house, they don't tie it together there. They only tie it at the service. The reason you tie them together is if you didn't have what they call bonding between the ground and the AC common, nothing would trip to ground. You'd have no safety, none of your safety circuits would work because there would be no connection. So there's always a bonding point. Now, what's interesting about this is that as soon as you have a transformer like this is the secondary side of this transformer is electrically isolated from the primary side. So this is considered a separately derived service. So it gets treated just like the panel in your house. The neutral is hooked to the ground. You see it right there? We have a ground wire hooked into the neutral block. Right? If we didn't do that, nothing would trip to ground. You could energize something and it would stay energized and not trip the breaker and go off and so you could get a shock. So this is probably the most left out thing I ever see in panels. It's amazing how many electricians leave this out, the bonding jumper out, and I've seen it in big buildings on big transformers and stuff, but it's really an important thing. And if you don't have that, in the case of like 3-phase, one phase can go to ground and won't trip. What happens to the other 2 phases? Well, now they're at the full voltage to ground. They're no longer 120 to ground. They're now 240 to ground, which means that if you touch one of them, it'll probably kill you. That's why this bonding jumper is so important. Okay? So again, when I am starting up a new panel, number one cause of a panel not starting when I first turn the switch on is a missing common. Number one. It's like you flip the switch and none of the lights come on. You say, okay. So you go looking for did they bring the commons to everything, right? That's like the number one cause.